Okay, today is the geometric probability, and we're also going to be doing something on the calculator called permutations. It's basically 2 days at once because these are such easy days. All right, so in geometric probability, basically you are trying to use geometry to figure out a probability question. Like, for example, when you are throwing a dart, we have to assume you are good enough to get in this circle, okay? Because if you can't, then we don't have something that it's out of. So we always make this assumption that at least you're going to be able to hit the thing. Then what's the probability you hit the spot you want? Okay, this isn't exactly random. You know when you're throwing it, because you're trying to hit the middle, right? Do you get how that's not random? Because random would mean you just like throw something up in the air and see where it lands, like you don't care where it lands. Or you let a machine, like pick a spot to drop it in this circle. But you're aiming at the middle, so we just have to like think that through, that this is not really a great example. Because if you were good at it, you are much more likely to hit in here if you're good at it than you are to hit in the whole rest of it. All right, but we make the assumption in these kinds of problems that you are going to randomly land inside the circle. And then all it boils down to is you have a big shape and you have a little shape. Let's say we talk about this little circle right there. And we say, what do we want over what's possible? We want to hit this little circle, and we find the area of that little circle. Yes, there's going to be a few formulas you'll have to know for today, stuff you should know already, like the area of a circle. Area of a circle is, do you have it memorized? Please tell me you have this memorized. Pi r squared, that is correct. But it's worthy of reminding me because a lot of kids, if you were tested right this second, a few of you wouldn't have known that. The area is pi r squared. So let's say that this little puppy, okay, well, maybe I should actually use this. It says the center of the circle is 0.5 inches. Okay, now this is the radius, which is kind of nice because then they just gave us the radius for our little pi r squared. So our area would be pi, also known as about 3.14, times the radius, which is 0.5 squared. That's the area of what we want. Would you agree that that's kind of a small area? Question? I believe it says the radius of the bullseye is 0.5 inches right there. Okay, so I was doing the little center area. Then that's what we want. So that goes on top, divided by what's possible. Do you get that what's possible is just the whole big circle? And the radius of that one is 15, so you would go pi r squared, and since r is 15, you go pi times 15 squared. Anybody have 15 squared memorized in their head? 225, very good. So it's 225 pi. And if I left this other one in terms of pi, it would have been 1/2 squared, which is 1/4, which is 0.25. And if I leave that as pi, I'd say pi. Now, I know that's kind of a nicky number still, but at least they both have a pi in them. That way the pi can cancel. Final answer, 0.25 over 225. And you'd need to simplify that down, and we'd have a calculator. So on the test, you would simply divide those two numbers. You could have just got a decimal for the top and a decimal for the bottom, but you might not have noticed that you could have canceled the pi. All right, I want to do another one like that. You do this yourself. Do you get that the circle does not have to be in the center? I know on a dart game, it's always in the center, but if I know that somebody's going to land in this circle because they're on the Wings of Blue team, that's in an Air Force Academy, you can join the jump team, and you get to jump out of an airplane like a bajillion times then, and you get better and better and better and better, and pretty soon you're doing those cool like things up in the sky. Somebody's strapping a smoke pack to your leg as you're flying in. Somebody else has got an American flag strapped to them, and then they like carry a football and they land at the football game, and pretty cool. Anyway, so let's say that again, we have to go with random. If you're trying to hit this spot, it increases the probability you would hit that spot, right? So if you just randomly are told, land in this circle, but they didn't tell you that they had this like little swamp over here, you know what I mean? Like this little area is kind of swampy, so you're not aiming for it. You just know you're supposed to land in the circle. Well, then what would be the probability that just by luck you would have happened to land in the little swampy area? All right, well, you'd need to know a couple things. Let's say the radius of this thing is 100 feet. It's a 100-foot radius. And let's say that the little swampy area has got a radius of 10 feet. Would you please figure out the probability that you'd land in the little swampy circle by accident, because again, you wouldn't be aiming for that. And it's what you want, the thing you want. And I know in this case, you don't really want to land in the swampy circle, but that's the thing we're investigating, so that's what we want. It's the probability of landing in the little swampy area, what you want, divided by all the things that were possible. And we made the assumption that you will land somewhere in the big circle. Again, don't forget you can cancel the pi's off. Save yourself some time on the calculator, because if you really understand that they both have a pi r squared in the top and the bottom, it'll make your life a little quicker and a little easier. All right, I'm going to pause for a minute while you figure this one out. And if you've got this, this is it. This is it for this part. It's what you want. Figure out the smaller shape. Divided by what's possible. It's always the bigger shape. I'll pause for a second. So since there's a pi r squared on the top and a pi r squared on the bottom, do you get the pi's can cancel? Why am I not going to just cancel the r squareds then? Because they're different. Pi is pi in both cases, but the r's are different. The bigger r on top, I just can't cancel those. All right, so, sorry, it's not the bigger on the top. The smaller one's on the top. So the smaller one was 10, so it's 10 squared over, the lower one was 100 squared, and so 10 squared is 100, over 100 squared. If you think about this, I don't even need to use a calculator, because isn't 100 over 100 squared is 100 times 100? You know what I'm saying? 100 squared is 100 times 100. So then, why did I do that? Because then I can cancel, and if you can cancel, you should. Just like if you can factor, you should. Final answer is 1/100th. So what is that for percent? 0.01. All right. Now, if you did this by figuring out an area on the top and then figuring out an area on the bottom, you still should have come up with 1/100th or 0.01. How many of you got 0.01? Awesome. Any questions? Any questions at all? All right, so then the problems just get weirder. Now this one, it's actually impossible as it is written. And I want you to tell me why, making the assumption the goat can't go in the barn, the barn doors are locked and stuff. Why can't we figure out this probability? Yes? Because some of the box is outside the circle. Exactly. Now, I think what the teacher meant to do when they made this problem was I think they meant to have the this circle here. Get how this is really 10 feet. Do you get that the goat really would only be able to go to here? You see what I'm saying? So they just drew the circle in a faulty way. The circle should go like this. And then again, if this is 10 feet, it should go to here. And I actually think what happened is sometimes when you convert these from a PDF to the smartboard or vice versa, it can mess up your shapes, like circles become a little smaller or get moved or whatever. So we are going to have to just adjust it that much. Now, do you get that Mr. Goat can't actually walk in the whole circle? How much of a circle can he walk in, though? Can he walk in half the circle? Yeah, he can actually walk in more than half the circle. He just can't walk in this part and the red part. So what percent of the circle can't he walk in? 25% of the circle isn't possible. So remember, it's what you want over what's possible. So the goat's area that is possible to him is not the entire circle. What he wants, the area that he wants to eat in, and again, if the goat actually really wanted the dandelions, then it would not be random. And he would be much more likely to go there because he actually wants to go there. But we're assuming that we have just labeled this little spot and the goat doesn't care about those more than anything else. So he just randomly happens to walk into that patch. Well, then it's what you want is that little patch. All right, I'm going to pause for a second to see if you can figure this out. The want's easy. It's what's possible this time. It's more complicated because it's not the whole circle. But I've given you enough that it shouldn't be too tough. Pausing. Okay, so what you want is 15. Good. And what's possible is obviously has to do with the circle. Did you figure out the area of the circle yet? Well, tell me the area of the circle again. What's that little formula? Okay, and in this case, the R is what? Okay. So now tell me what's the area of the circle again? And say it in terms of pi, as in like 45 pi. But you can do it. What's 10 squared? There you go. So what's the answer? 100 pi. That's all I'm saying. Okay, good. So it's 15 over 100 pi. But that would be if he could get to the whole circle. Can he actually? Is that possible? No, it's what we want over what's possible. So then, tell me, Mr. H, what part of the circle can he get to? Because we need to put a fraction in front of this circle. He gets 3/4 of that. Can you do that in your head? I bet you can. There you go. So final answer in terms of pi, as in leave a pi in your answer. What's on top? There you go. Could that be simplified? Sure it could. But that's pretty much it. From there, it's just simplifying. Could you have subtracted 1/4 of the circle? Sure, but I think it's even smarter to do what he did, which is take 3/4 of the circle. All right. So that one was a tricky one just because there were things that wasn't possible. All right, this one. There's a whole bunch of places that are possible and places that are not possible. Really what you want over what's possible. Take the time, figure this one out, do it all yourself, use a calculator. And I know some of you are going to be like, but you have to tell me the radius of the circle. They actually did. If you think about it, you can figure out the radius of those circles. They told you enough info. All right, I'm going to pause for a sec. Take your time, figure this out. Okay, let's see how far you've gotten. Kids were distracted a little bit because I had handing back tests there, but row 5, person 3. That's you, Mr. Z. Tell me stuff you've figured out so far. Area of a blue circle, that's a critical little element. Well, first of all, you must have figured out the radius of the blue circle. How could you do that? Because they didn't tell you, but they did. If the diameter of each one was 1, it would add up to 4. Perfect. Okay. So then if the diameter is 4, what'd you use for the radius? Perfect. How many of you figured out that each of those little radii was a half? Okay, good. So then tell me how that informs this problem. I have a want over possible. What do I do? All right, so each circle is pi r squared. So pi times 0.5 squared. Okay, I like it. But then there's a lot of circles, right? So I got to put how many circles in front? How many circles were there? 16. So I go 16 times pi times 1/2 squared. Nice. Divided by what's possible. What's possible was everything, and that's actually much easier. It's 4 by 4. Makes a total area of 16. And then notice, the 16s will cancel. See that? Don't always just blindly put this into the calculator. Look at what you got, because it'll be much easier to put in now. Those 16s can cancel. So now I got pi times 1/2 squared. 1/2 squared, I can even do that in my head. It's 1/2 times 1/2. What's that? 1/4, and I know the decimal for that, which is what? 0.25, and the only thing left is the pi, 0.25 pi. The reason that that's also smart to do is on the ACT test, for example, a lot of times they'll leave their answer in terms of pi. You go through and get the answer, and you get this answer of like 0.734, and it's not on the list. It might be because they have their answer in terms of pi, like this. Okay, yes, sir. Our tests are usually not multiple choice, and therefore you have to figure out the answer. And therefore, in the directions, it could say it wanted an exact answer. That would be the one that has pi in it. You get how as soon as you change pi to 3.14, it's not exact anymore? Okay, so that would be the clue that they want an answer that's got pi in it, is if they would say exact answers only. And as soon as you find yourself rounding a decimal, you must be like, that's not exact anymore. That's when you should go back and leave your answer with a pi in it. So this would have been okay answer, or the actual decimal answer, which would have been 0.25 times, I will accept 3.14 as an okay estimate of pi, and then your answer would be some decimal that's like that. Yes?
Wait, so is that the probability of picking out a circle or like the yellow?
Okay, remember this is a decimal when we're all done, and that's the probability of landing in the circle. Are we not supposed to find the probability of landing in the circle? Oh, I didn't even read that. I assumed we wanted the area of we wanted to land in the circles. We don't. Okay, that changes everything. Thank you for catching it. All right, we just found a probability. It's a great one. That's not what they asked. But we can use some of the data that we have anyway. Do you get that what we want was right? That one was right. It was out of 16. With me so far? All right. What's possible was 16. What we wanted was not those circles. So then we wanted to do, okay, there was 16 of those circles, that was still important. 16 pi 0.5 squared. But we wanted the part that was not in the circles, which would mean who can fix this? It's a simple little thing to fix it. We don't want this. Yes. Yes. We take 16 minus 16 pi, blah, 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 blah. Okay? That'll mean 16 was the total, and we take away the area of the circles, we get the other area. This is what it always boils down to, is you have a bigger shape, smaller shapes, and you're always going to be subtracting the smaller ones from the bigger ones. Now, this one, I thought we just wanted the circles, which again, didn't even involve any subtracting. It involved in figuring out this small shape and multiplying it up a whole bunch of times. There were 16 of the circles. But, long story short, thanks for catching that. Your answer would be a decimal. Again, if you can factor it, you should. You remember that deal? I can factor a 16 out of the top. And 1.5 to the 1/2 power is, to the second power is 1/4. So this is 1/4 pi over 16. And why did I do that? So this stuff cancels. Boom. Now it's 1 minus 1/4 pi. That's just me showing how you could have factored the 16 out of the top so that you could make it cancel with the bottom. And then if you needed an answer that was perfect, that would be it. All right. Remember that these always boil down to what you want over what's possible. And I'm not going to continue with this part because I think that's all you needed to know. It's always the bigger shape divided by the smaller shape. All right. Now I'm going to stretch us a little bit and have you do a second lesson today. So I'm going to pull that up now. I'm going to pause while I do that. Okay, so this is the right file for the next day. Permutations and counting. I'll give you a minute to get there before I ask you to show me that you found it. This is the next day's less. Okay, a permutation is a really fancy word. And it is about how many sets you can have. All right, I'm going to have a set of 3 things up here. I'm going to have phone. I'll use my phone so nobody gets paranoid, but I'm going to drop their collateral phone. I have phone, I have remote, and I have bottle. Okay? With these 3 things, think of them as like books on a shelf. You could go, going from left to right now, we have remote, phone, bottle. Remote, phone, bottle. Do you get, I could rearrange them. That is called a permutation. When you just rearrange something, that is a different permutation. Okay, so I'm going to move the remote over here, and now here's a different permutation of that, and it's phone, bottle, remote, because I moved the remote over to the other side. Can you name any other possible orders they could be in? Not super hard. What hasn't been first yet? Bottle. Here, I'll move the bottle over. Now it's bottle, and then phone, and then remote. Is there any other possible permutations of this? Yes. Phone, remote, bottle. And that would look like this. Phone, remote, and then bottle over here. Okay, cool. What else you got? There's more. Yes. Bottle, remote, phone. Bottle first, then remote, then phone. Okay, we have them all? No, there's one more. Yes? Remote, bottle, phone, B for phone, remote, then the bottle, and then the phone. There. Do you see how with only 3 items, there was still a lot of thinking involved to get this? Do you get that if I was talking about taking everybody in this class and lining you up out in the parking lot in a certain order, okay, there's 30 of you, do you get there would be almost an endless combination of different ways we could line you up out in the parking lot in one big long line? Kind of like I was doing with the remote and the phone and the bottle. Okay? It would be insane. Well, there's a calculator function that'll do this for you. Okay? And I'd like you to grab your calculator and find under Math, the Math button, find the button or the choice called PRB for probability. Math, PRB. I'll pause while I get. Okay, so let's say I wanted to do the one I just did with the bottle and the phone and the remote. Okay, there was 3 items. So if I was going to do that, first of all, I would say I have 3 items. Everybody go out to your main screen and just hit a 3. Yeah, then you were going to put in that P for permutation. So that's under Math. Arrow over to probability. It's 3 arrows to the right. See how it says PRB at the top? They're like tabs. And I hit enter. And I just did the wrong one. Sorry. That is, I don't want a random number. This does generate random numbers, which is kind of cool. You can have it generate a random number between like 1 and 10 or whatever, but I just screwed up. I'm going to try again. 3. And then I should do what I just said, except not actually hit the button. Math. PRB for probability. And now it's that one, not the random one. NPR. And mine goes like this. If you have an older version, it says 3, and then it says NPR, and then it's waiting for you to type the other number, which is, and this is important now, there were 3 things. It's how many of them do you want to line up? Do you get that if I have 3 things, I could just take little sets of 2 and say, okay, 2 at a time, there's this way, or there's this way. And then I could take these back and put out these 2 or those 2. So I mean, you got to know how many do you want to line up. If I want to line up all 3 of my things, then I do 3P3. And I hit enter, And we just figured it out a second ago. We made a list of them. There were 6 of them. There's how we get your answer with the calculator. All right. Imagine for just a moment that I add a 4th thing. Now I'm going to add calculator to my little things that are up here. Okay, and I'm going to do all 4 of them. Rearranging those 4 things. Think of it as books on a shelf, because they're going to ask you that question. Books on a shelf. These are like 4 books on a shelf. Could you put them in a different order? Sure. How many orders could you put them in? That's a permutation. Let the calculator do it for you. I have 4 things. I want to line up all 4 things. 4p4. Figure it out. This time we don't have to list them all, which would be the sample space. This time we just have to say the answer. Okay, so 4p4. 4 math probability NPR 4p 4 enter. If you get 24, raise your hand if you got a 24 on your calculator. Good, then you know how to type these in. Okay, now what if I had my 4 things, which again are bottle, phone, remote, and calculator. What if I was going to only take 2 at a time? I only wanted to take 2 things at a time. And then how many different permutations would there be? Again, bottle, phone is different than phone, bottle. That's because it's a permutation. Tomorrow we get into these things called combinations. Combinations are simpler because if you take 2 things, you don't have to like say different ways you rearrange them. All right, so if I take these 2 things out in a permutation, I care about the order. In fact, I'll add this dumb little saying because you're going to get confused between permutation and combination. Permutation, the order matters. The order matters. I'm trying to make you remember that P goes to the order matters. Order matters. I know it's dumb, but it'll probably help. You'll be on the test, you'll be going combination, permutation. Which one does the order matter? Order matters. Oh, P. The permutation is the one, the order matters. Okay, so back to, if I have these 4 things and I'm going to choose out 2, would you please do 4P2? 4 math 4P2. I'm going to call on a random person, figure out 4P2. You know how to do it on your calculator. All right, I'm not going to do random people that right this second. I'm going to call on individuals. Be ready. There's some people that I'm suspecting aren't actually typing this into the calculator. Now I'll feel bad if I call on anybody in particular, so I'll let the dice do it. Row 6, 5th person. That's you, LD. 12, raise your hand if you had 12 for that one. Awesome. And I go over to probability, and I go down to P, and I go enter, 4P2, and there it is. All right, now I'm going to give you a word problem, and you can use your calculator to figure this out. Okay? Let's say I'm going to get 6 toppings on my Subway today. 6 things that I like. Do you get that I probably really don't care what order they put them on my sandwich? But they could put them in a whole bunch of different orders. They could put the meat on first, and then they could put on you know what I mean? Or they could put the mayo on first and then put on the meat. Or they could, it doesn't really matter to me, but if I'm doing how many different ways could they make that sandwich with, how many did I say? 6 toppings. Do I only want them to put on 2 toppings? No, I want them to put on all 6. So it's 6P6, figure it out. There's a lot of ways they could make that sandwich. 6 math probability P6 enter. 720 different ways they could make that sandwich. Okay, then one more. This whole class goes out to the parking lot and lines up in order. If the entire class could be reshuffled into different orders, and there are, I'll count you, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Screwed up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. There's 32 of you. Would you please tell me how many different orders I could put all 32 of you in? Isn't that a huge number? It's so big that the calculator cannot display it on its screen, so it gives me scientific notation, and it's saying take the decimal and move it, how far? 35 places. Isn't that insane? But it's true. Do you get that actually to rearrange you into every possible order, it would probably take us like 2 weeks? It's like 24 hours a day just rearranging people. It's insane. It's true, though. Because you would think there's not that many orders, but there are. All right, this is one of those reasons that, again, winning the lottery, so unlikely, because actually it's not. The order doesn't matter. If you've got the numbers, they don't have to be in the order. I don't think they have to be in the order that you call them off on, do they? You think they do have to be in that order? Oh, you know, I think you're right. And again, that's another of those things where it makes you feel like you have a chance of winning this lottery. It's only like 12 numbers or whatever. But how many different ways could they have them in order? Insane number of ways they could be in order. So, all right. So, one more combination like this, or sorry, permutation, is if there's 32 of you and we run across the parking lot, do you get if we took first, second, and third place, you know, like a speed test, a race, first, second, and third place, we could do 32p3 if we only cared about first, second, and third place. Try that one. 32p3. Still a really big number, but not near as big. What's the difference there? I'm only caring about 3 of them then. Pulling out groups of 3. There's still 29,000 plus, I'd probably round it to 30,000 different ways you guys could finish first, second, or third. Let's get it down to a smaller number because people understand those a lot better. Let's say that there are 4 people, and you're going to race, and only first, second, and third place matter. If there's 4 people, and you're only going to keep track of first, second, and third, how many different ways could Bob, Sarah, Jim, and I'm trying to go for gender equality here, so we'll say Mary. How many different ways could they finish? All right, so that was 4p3. I'm going to go 4 math probability b3 enter 24 different ways, and that's only with 4 people. There's 24 different ways they could finish first, second, and third. All you got to do is rearrange one of them, and it's different, right? And then move somebody to the beginning that wasn't the beginning before. Again, even that's kind of counterintuitive. Most people wouldn't say there was that many different ways that those 4 people could finish first, second, and third. All right, so here's my question. What if there's 4 people racing, but there's one person who's clearly going to win? Does that change the probabilities? If you know, you guys know this. If there was, I could probably pick 4 of you, and we could probably pick it such that, oh, this one kid, there's no doubt they are going to be the fastest. So they're going to win out of those 4. How do you change your probability because of that? Well, here's how you do it. You use blanks. If there's first place, second, third, and fourth, and if we say that Bob is going to be first, then there's only how many choices, and we will multiply our choices together. How many choices are there for first place? There's only one choice. Bob's going to win. The other way they'll say this question sometimes, is they'll say it's a batting order, and they really want Bob to be first. So there's only one choice for that first spot. Now, there are 4 people. You might think there's only one choice, one choice, one choice, one choice, but then the answer would be there's only one way you could do it. That can't be right. So think of it this way. If Bob has to be first, but all the other spots could come in anyway, we don't know how they're going to come in, first, second, and third. Then how many different choices are there for second place? 3. How many choices are there for third place? And now for fourth place, there were only 4 people. We've already got 3 of the 4 placed, right? Do you get it? We just times by 1 at the end because there's only one person left, and they're kind of like, they have to be in that spot. All right. So this is also used for license plates. Do you know there's 3 letters and 3 numbers in Minnesota license plates? And in the old days, it was letters first. Now I'm pretty sure it's numbers first. Can anybody verify that, or is it letters first still? Letters first? Is it still letters first? Okay, cool. All right. I remember in the old days, my license plate was Fez 470. I loved it because it had a ring to it. Like I could say Fez 470. I knew what my license plate was. All right. Well, how many different combos are there? There's a lot. Because there's 26 letters, right? There's 26 choices for this first spot. I would not do this with permutations. I would do this with multiplying choices. So when they tell you some tricky stuff like, oh, this book has to be first, make yourself a bunch of blanks and then multiply choices. There's 26 letters, right? So it's 26 choices for the first one. Now, can you have the same letter on the license plate twice? You actually can. Yep. You could have QQQ if you got lucky. All right. So anyway, 26 times. How many choices are there for the next number then? Or sorry, the next letter then? 26, because there's 26 letters in the alphabet. And it can repeat. Times another 26, because that's the third letter. Now, how many choices for the numbers? 10 for this number. How many for the next number? 10, because numbers can repeat too. And then how many choices for the next one? There's still 10 numbers out there to pick from. It's not like we had a limited choice like we did before where there was only 4 people and this had to be a 1. There's still 10 numbers. It's 10. Now, some people are confused why there's 10 digits. Remember, it's 1 through 9 would be 9 digits, right? And then a 0 makes the 10th choice. So there is 10 choices for each number spot. That's how many different license plates the state of Minnesota can have. It's a lot. But they do take some off. Like the FU, there's a lot of options that are not really ones you would want on your license plate. Okay? They do have some on there that are like FAT, fat. It may not be too happy to have the fat license plate, but yeah, you might get stuck with it. Okay? But there's a lot of them that they have taken off. I'm going to pause the video for a second. So if there are license plates that are removed from this is how many license plates there would be, but they take off all the ones that are inappropriate, then all of a sudden is less. But honestly, in the big picture, there's only a few hundred license plates. There is actually a list. The state of Minnesota has a list. Here are license plates you may not have because they're naughty, mostly. Some of them are actually for the cops because it's hard for them to discern between like 0880, like they're maybe palindromes or things that are like complicated, might mess with your head. Try to remember that license plate. If you only get a quick glance at a license plate. Anyway. So, yeah, zeros and O's and that kind of stuff. All right, so that's it. You have now learned everything that you needed to know about. And I'm going to summarize it quick. Here's a super simple, typical, I've got a circle. There's a square inside of it. This is a side of 4, and the circle has a radius of 7. And then they might say, what's the probability that you randomly land inside that square as you're, dropped from a plane? If you know you're going to land inside the circle because you have to, because you can't fly that far, this way or that way by skydiving. There's only so far you can track, it's called. Well, then that's a typical question, and it's what you want over what's possible. All right, what we would want would be that square, which would be 4. Area of the square is 4 times 4. Over what was possible is pi r squared, and the radius was 7, so it would be pi times 7 squared. That's a typical one. And then the other one is about permutations. You got to know that button on your calculator, the NPR button. And if I said this, 8P3, that means there's 8 kids, and we're only going to be taking groups of 3, and it's how many different combinations. These aren't even probabilities. Think about it. They're really big numbers. But we use them later to do probability questions. For right now, we're just teaching you how to count how many total would there be. If there was 8 people and we're taking first, second, and third place. And then also on the permutations, don't forget to use blanks, and you multiply your choices. Okay? So if I say, I want Mary to be first, there's only one choice for the first spot then. Because you said Mary has to be first, there's only one choice. And if I want Bob to be second, we're like lining up for pictures, and this is like wedding pictures, and they have to be here and here. There's only one choice and one choice. Then the rest of them, let's say there's 10 people total, there would be 8 people to choose here and 7 people to choose there. If you're forced to pick out of your 10 these 2, then there was 8 left, and then because we picked 1 for that spot, 7 for that one. All right, so that covers pretty much everything you need to know. Now, for the next 2 days, we're assigned 2 different things. One of them is the Schoology quiz on, what's it called again? The probabilities, the area probabilities. So I think what I'm going to do is assign just that tonight. And then tomorrow, when you come to class, I will do a quick review of the permutations thing and then assign that, and then we'll have a bunch of time to be able to do the Pi Day celebration a little late this year. All right, so would you please find the Schoology quiz for today's date, which is 5/7. Pausing while we do that. Okay, it looks like this. A target for archery practice. Assume an arrow lands in the circle. And again, I have an issue with it right away. The issue is randomness. If this is really a target, then you're going to be aiming at something, which does not make it truly a probability question. Get what I'm saying? Just reminding you. Yeah, unless they cover your eyes. But then I don't know how they would make you hit inside the circle. So anyway. All right. So what's the probability the arrow lands in the circle, but not in a square? Remember, it's what you want over what's possible. So what do we want? We want in the circle, but not in the square. Circle minus the squares. All over what was possible. The circle. That's kind of the big picture. Now let's figure out the area of the circle. Then we'll subtract off the area of the squares. What's the area of the circle? Pi r squared. And what's the r? Be careful, it's not 36. 18. Okay. A lot of people have that one memorized, which is awesome. That's the area of the circle. Each square is 25, but be careful you don't put 25 there. You got to put... There's 4 squares that we have to subtract off. 4 times 5 times 5. And that's all divided by the area of the circle again, which was pi times 18 squared. Careful you don't think we can cancel this, because why can't we? Because it's part of a subtract problem. See what I'm saying? So you need to actually figure out, don't cancel that, don't cancel that. You need to actually figure out this. Get your answer as a decimal, then divide it by that. Yes, sir. Pi, I'm fine with using 3.14. And wait a minute. Let's make sure that that actually works, because if the key, since this is done on a Schoology quiz, I don't want it to mark you all wrong for using 3.14. It's possible, I know it says around 3 decimal places, but that also means that you shouldn't round in the middle of a problem. I'm going to change that. I would bet you money, I know the person who made these, and I bet you money they're going to ask you to use the pi button since you're allowed a calculator. So in other words, don't use 3.14. The pi button is right above the caret. See it? Here, I could show you this. The pi button is right here. It's right above the little caret there. That's 3.141592653589793323 blah blah blah. Okay, so that way you won't possibly get these all marked wrong because of a little rounding mistake. Hate to have you do it twice because of that. So to be on the safe side, do that. At the very end, you round your decimals. At the very end, you round your decimal to 3 decimal places. Okay. Just have that part done for tomorrow. And tomorrow, I've already taught you the lesson. I'll just give you a quick reminder on how those permutations work, and then we'll have the fun day. All right, that's all I got for you for today.